11:15, 16, it's November 15th, and we're going to start to talk about electron configuration and how we express it. So we talked about where electrons live. Where do electrons hang out? What's that three-dimensional region of space? Yeah, orbitals are where electrons live. But to know how those atoms are going to behave, we have to know a little bit more about which orbitals they're in, how high the energy is for those orbitals, and to just kind of get a sense of how to express that, because that governs everything about how atoms behave. So what we're going to start to talk about are called electron configurations. I typically, the shorthand that I use for electrons is E with a little negative sign, and that's pretty common, actually. So the electron configuration of an atom is its arrangement of electrons. That determines how it behaves, and there are 3 rules. If you're a rule-following kind of person, you're going to like this, because there are only 3 rules, and if you follow those religiously, you will not mess up your electron configurations. Easy breezy. The first rule, the Aufbau principle. I think of it as a lazy electron rule. Okay. An electron will occupy the lowest energy orbital that has a spot for it. 1s is the lowest energy orbital, 2s is next, 2p is after that, and then we start to get weird. It starts to do some overlapping, and this is one of those things that they don't teach you in physical science. So I very often use a metaphor of a building, and actually I would change one thing in this drawing. I'm not doing a great job drawing this, I apologize. We can think about this kind of like a high-rise building. Many of you will be moving into dormitories in the next 2 years. If you're going to go away to college, you may end up in a high-rise. And the idea is this. On move-in day, if you got to pick your own room, and you're walking in loaded down with your backpack, your dorm-sized refrigerator, all your books, and your suitcases, and your mirror, and your whatever else you're bringing with you. If there's a room on the first floor, you're not going to climb the steps. You take the lowest energy room available to you. Because it takes energy to go to a higher level. We're assuming there's no elevator here. It requires energy for you to climb up. So this is the lazy electron principle. An electron goes to the lowest energy orbital that will take it. And like I said, I think about this like a high-rise dormitory. On the first level, there's only 1 room. On the second level, there are 2 rooms, and one of them happens to be subdivided into 3s. This is the 1s, this is the 2s, 2px, 2py, 2pz. That'll become important in a moment. Okay, so you're not going to climb any more stairs than you have to. Great. Well, there's a catch. And that catch is that the amount of energy it takes isn't always as linear as we would like to think. This is called the Aufbau diagram, or the electron filling diagram. And you're going to get really good at constructing this. You're going to get good at drawing this. And you're going to draw it on every test you do for the next couple chapters, honestly. I'll even give you a few points on one of your quizzes for drawing this. Like, construct this, you get 2 points. You have to construct it anyway. So what this does, it's weird, but if you draw the subshells in this very particular order and put arrows through them in a very particular way, it actually tells you the order in which they fill. I don't know who figured this out. I don't know how they figured it out. It seems too weird to be, and too coincidental to be true, as though the cosmic fabric of the universe is somehow doing origami tricks. I don't know. We're going to practice drawing this together. Okay, we start with 1s. Directly below it we put 2s, and then we put 2p. Directly below 2s, we put 3s, then we put 3p. What orbital, what's the next orbital what's the next subshell on the third main energy level? 3d. So we put a 3d. Directly below 3s, we put 4s, 4p, 4d, and then what comes next? 4f. Well, right below 4s, we put 5s, 5p, 5d. What did I just do? 5f. Now, we could put 5g here, but we usually don't bother because the odds of you having an electron that has any, or an atom that has any electrons on the 5g sublevel is ridiculously slim, and you're going to see why in a minute. We'll practice with a few really big ones. Okay, so then 6s, 6p, 6d, 6f. Again, we could do, 6g, and whatever comes after g, I don't know. I don't know if anybody knows. I sure don't. We generally don't mess with those because, like I said, the odds of you getting an atom that would need to put electrons there are slim to none. Okay, and then we usually do 7s, 7p, 7d. You can do 7f. You'll notice that the one that I showed you it stops at 6d and 7p. And that's totally acceptable. Now what you want to do, and if you've got colored pencils or you're using Doceri, it's nice to use a different color so that you don't obscure the letters underneath. And I'm actually going to do this in a really light, bright blue. So you draw an arrow, and it starts off going through the 1s, then it goes through the 2s, through 2p to 3s, through 3p to 4s, through 3d, 4p, 5s, through 4d, 5p, 6s, through 4f, 5d, 6p, 7s, through 5f, 6d, 7p, and that's usually where people stop drawing. You can go ahead and continue, of course. Then, you know, in reality that would start with the 5g. So that's a good place to stop if we wanted to do that. Those exist, but we don't talk about them. We just don't talk about them. What this gives you is the order in which orbitals fill, or subshells fill, rather. So, I'll go to red for this. What's the first subshell to fill? 1s. What comes next? Follow your arrows. 2s. I'm going to shrink this and move it around a little bit. After 2s, what's the next subshell to fill? 2p. Then what? 3s. After 3s, we go to, you're all looking at me as though you think there's a leg hold trap laying in the vegetation. There is. We go to 3p. There is, but we're not at the trap yet. Now we're at the trap. What fills after 3p? 4s. It's not 3d. We think 3, 3, 3, 3, 4, 4, 4, but it's not. We have this weird little thing that happens, and you have to be really careful when you're doing this, and that's why you will start to draw the subshell filling diagram on all your tests so that you don't screw that up. So after 4s, what fills? 3d. Then what? 4p. Then what? 5s. What? It's true. You'll get really good at this. The analogy of the high-rise building breaks down a little bit, but what you basically have to think of is that this is a building that's built into a hillside, and there are some rooms on the 4th floor that are lower than rooms on the 3rd floor. So it's strange, but if you draw this diagram every time, you will never screw this up. That's the first rule. Low energy first. Okay, rule number 2, the Pauli exclusion principle. This is named for Wolfgang Pauli, another of the German particle physicists. Interesting guy. So what Pauli exclusion says is that no 2 electrons can have the same address. We can't have 2 electrons that have the exact same address. And if we go back to the dorm room metaphor, in every dorm room there are generally 2 occupants. And if we want to get a piece of mail to them, we need to specify if they're occupant A or occupant B. Bed A, bed B, something like that. So we need the building, we need the floor they're on, we need the room number specifically, the shape of the room number, and then we need to know, are they A or B? In electrons, what this is all about is that every orbital has 2 electrons, or can hold 2 electrons, but we have to differentiate them somehow, and we do that with their spin quantum number. And we identify spin as being spin up or spin down. I want to make it really, really clear that this is not, you should not be picturing little electrons that are spinning like a hamster wheel. It's not what's happening. But that's what we think of when we hear spin. It's a particle physics thing, and it's kind of beyond any it defies description. But we designate them as spin up and spin down to differentiate them. So if we have 2 electrons in the 1s orbital, and our first form of writing configurations will literally draw out each orbital, and if we have 2 electrons here, we'll say, well, we have that, 1 up and 1 down. And then if we have some, in the 2s, we can say we have 1 up and 1 down. And if we have some in the 2px, the 2py, the 2pz, well, before we can do that, we have to go to our next rule. So the next rule, rule number 3, it's called Hunds rule. I care less that you know what these are called, Aufbau, Pauli, and Hunds, than that you know how to use them. Hunds rule says that for every orbital of equal energy, it gets every orbital that has equal energy gets 1 electron before any of them get 2. And I think of this as the no roommates until we have to principle. So again, to go into this metaphor, and I'm going to copy my little tower. Copy. Paste. So in this little tower, if you, as an electron, walk in and you get to the first floor and there are already 2 people there, you can't live there, you have to climb stairs. And you have to go to the 2s energy level. And, well, actually, no, let me change that metaphor a little bit. Let's say you get to the first floor and there's 1 person in that room. Just 1. There are 2 beds. You could live there. If you don't want to have a roommate, you have to climb a flight of stairs carrying your dorm-sized refrigerator. You know what? I can live with a roommate. It's fine. I'll be fine right here. If you get up to, and I'm going to try to expand this. Can I do it? If there are already 2 people on the first floor, 2 electrons in that orbital, so you have to climb the stairs. You get up to the next orbital that can fill, the 2s. and there's nobody there. Well, you move in. That's easy. What if there's one person there already? Well, here's the deal. There are actually a couple of stairs in between the s and the p. Those two p orbitals are slightly higher energy. So you would actually have to climb a few stairs to get up to the p orbitals. So you stick with the s. Take your 4 minutes, we'll come back. Okay, so refreshing, Hund's rule. If you don't have to take a roommate and you don't have to climb any more stairs, you won't. When we have orbitals that are equal energy, every orbital gets 1 electron before any of them get 2. So, that was our little example. Let's go back to here, because we started to say, well, okay, what would happen next? We filled 1s, we filled 2s. Let's say that we have 3 more electrons to distribute. The question is, where do those electrons go? 1, 2, 3. Because every orbital of equal energy gets 1 electron before any of them get 2. So let's do some practice. I'm going to copy the subshell filling diagram. Subshell filling, that's what we call it, not electron filling. Silly me. And we'll paste that in here. And we're going to do, so the first format that you're going to learn 3 different formats for writing electron configuration. The first one is called orbital notation. So orbital notation means that we literally write every single orbital. It's a giant pain in the butt. By the time you get good at this, you will hate it. Because if you're somebody who likes to take shortcuts, you're going to hate orbital notation. So that's a fair warning, because when you're doing orbital notation, you can't take shortcuts. You actually have to write every orbital. Once you master this, you can go on to things that allow you to skip this altogether, and that's fine, but you do have to learn this format first. So in orbital notation, we draw every single orbital, we write the orbital name underneath, and we put our little electrons on every orbital with up and down arrows. I usually do the half-headed arrow, but you don't have to. I just find that an easy motion to make. It's a single stroke, that. Easy, easy, because I'm lazy too. All right, so orbital notation, let's practice with an atom that has 8 electrons. So grab your periodic tables, get those out. Okay, you've got your periodic table. So what element are we talking about if we're talking about something with 8 electrons in a neutral atom? We're talking about oxygen. There she blows, right there. So, what is the electron configuration for oxygen? Writing it in orbital notation. We're going to start out with the lowest energy orbital that exists, 1s. I'm going to go ahead and write my orbitals out. 2px, 2py, 2pz, 1, 2, 3. So I've put in my first, 1, 2, 3, 4, my first 5 orbitals. That'll take me up through 10 electrons. That's all I'm going to need. So now I'm going to write in my electrons. Where do my first 2 electrons go? 1s. I just like making that sound when I do electrons. Like little whips. Where do my next 2 electrons go? 2s. How many electrons do I have left to place? Check your math. 8 electrons. I have 4 in. 4. Okay, somebody else said 3. So we have 4 electrons left to place. What does this look like? Let's do them one at a time. Where's the next electron go? 2px. 1. Next. 2py. Next. Now what do? 2px is going to get a roommate. That's it. That's the orbital notation for an atom with 8 electrons. So let's do a couple more together, and then I'll turn you loose to practice some. Let's do the orbital notation, show the electron configuration using orbital notation for an atom that has 15 electrons. What element are we talking about here? Okay, so 15 electrons. This is going to take us up to the point, is this going to take us up to where we have, oh, no it won't. Okay. So, 1s, 2s, 2px, 2py, 2pz, shoop, shoop, shoop. 3s, what does that take us up to? 1, 2, 3, 6, 12. Won't quite get us there. I'm going to move this down and over. 3px, 3pz, 3py. Okay, that should get us to where we need to go. So, first 2 electrons. Where do they go? Next 2 electrons. 2s. 1, 2. Next 6, how many electrons do we have left? We've filled 4. We have 11 to go. So, do we have enough to fill the 2p subshell? Yeah. But I'm going to caution you on something. Don't get sloppy. Still do this. 1, 2, 3, 1, 2, 3. It will pay dividends later. Don't assume, I got this filled, and just put them in doubles. Don't do it. Okay, so now we're up to 10. We have a 3s. So, yep. 1, 2. We're up to 12. How many do we have left? 3. 1, 2, 3. And just to do a quick bit of differentiation, a quick bit of distinguishing. This is your entire first main energy level. It's a single subshell and a single orbital. This is your second main energy level. It's composed of 2 subshells, the 2s and the 2p subshell, and it's composed of 4 orbitals, 2s orbital, 2px, 2py, 2pz. So there are 3 layers there, and that corresponds to those quantum numbers. We only deal with the first one, but there are 4 total quantum numbers. The last one, of course, is spin. Okay, on the 3s, or on the 3, are we showing the whole energy level, the whole third energy level? No. What are we missing from the third energy level? D's. We're not showing the D's. We haven't gotten to the D's yet. Okay, let's do something that has a crossover. Let's do something that has 26 electrons. What element are we talking about? What would have 26 electrons? Iron. It's a weighty question. Okay, so 26 electrons. How far out do we have to go here? After 3p, what do we fill next? Look at your subshell filling diagram. So 1s, 2s, 2p, 3s, 3p, 4s. After 4s, what are we going to fill? 3d. Now, how many d orbitals are there? 5. There are 5 d orbitals. Any place there are d orbitals, there are 5 of them. So, we usually just write 3d1, 3d2, 3d3. I'm going to run out of room. Okay, a little bit messy, but it'll work. Do you have an arrangement of orbitals that looks like that? Okay, start filling. The first 4 are easy because they're S's, so you know that you're doing them, 1, 2, 1, 2. Then we get to a P, 1, 2, 3, 4, 5, 6. So we're up to 10. We have 16 left to go. S's, easy. 3P, 1, 2, 3, 4, 5, 6. Now we have another 4S. 1, 2. And I always have to stop and count how many I've got. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I have 6 to go. 1, 2, 3, 4, 5, 6. You should have something that looks like that. Even if we had something where not all of the d orbitals had electrons in them, we still have to show. Once you're showing a subshell, you have to show all the orbitals in that subshell. Okay? Do you want to practice a few of these on your own? And then I'm going to, in the time remaining, I will introduce the second way of writing these, which is a shortcut to doing this. So I want you to practice these first. And there are some problems in the book I'm going to give you. And then we'll shortcut. Okay, so we're going to start talking about the second way to show electron configuration. Electron configuration is how they're arranged. Notation is how we write that arrangement. So the first one we learned was orbital notation. Now we have what's called electron configuration notation. And this is a shortcut way of writing it. Each way you're going to learn gets shorter and shorter. So with electron configuration notation, all you have to do is write the sublevel. That's all you have to do. And then the number of electrons in that sublevel go on as a subscript. Starting out, most people are not comfortable just writing this, and they have to still write the orbital notation and then copy from the orbital notation, which is okay because in general, starting out, I'm going to ask you for both. So you're going to have to do them both anyway. As your brain just gets more accustomed to where electrons live, you're going to be able to go straight to this. And once I teach you some shortcuts in the next chapter, you'll be able to go to the shortest method of them all, because you'll just be able to look at a periodic table and immediately write the electron configuration. Whoa, it's true. That's some cool tricks. So you still have to write the subshell filling diagram, and I'll show you why in a second. Let's, well, you know what? Maybe we shouldn't start with that one. Let's start off with something that's got 8 electrons, and we had already done 8 electrons. This is what element? Oxygen. And we wrote the configuration, or the orbital notation, 1s, 2s, 2px, 2py, 2pz, 1, 2, 3, 4. Whoops. 4. So now I want to go ahead and write electron configuration notation. All I'm going to do is write the name of the sublevel. So I'm going to write 1s. And as a superscript on this, I'm going to write the number of electrons that are in that subshell. So this is going to be 1s2. Do not say 1s squared. Don't do it. It's not squared. You're not squaring anything. You're saying that there are 2 electrons in the 1s subshell. Okay, so the next subshell up is 2s, so I'm going to literally write 2s, and there are 2 electrons in it, and I'm going to write 2. 1s2, 2s2. Now, the next subshell I have is the 2p, so I'm going to write 2p, and I have 4 electrons there, so I'm just going to write a superscript 4. So when we state this, when we tell somebody what an atom's electron configuration is using electron configuration notation, we just say, yeah, it's got a 1s2, 2s2, 2p4. Okay? And like I said, we'll come up with some other shortcuts for that in a little bit. Let's shrink this, and let's do one that's a little bit hairier. And let's go ahead and do our 15 electrons. What was that? phosphorus. I don't expect you to have these memorized, but I do expect you to have your periodic table out. So phosphorus, and I'm going to actually kind of cheat and go back and copy my phosphorus. Whoops. Paste. Well, that's kind of, oh no, okay, that's fine. So this is the one where I had demonstrated all those sort of levels of division, the subshells and the main energy levels and the subshells. And that's pretty easy if we're doing this. So we have 1s2, and we don't usually put commas in there. 2s2, 2p6, 3s2, 3p3. Make that 6 a little bit neater. So that's how we would write the electron configuration notation for phosphorus, for something with 15 electrons. Now, I was leading up to the bad boy at the bottom, our iron. And this one is interesting because, of course, we have overlaps. So it starts off just the same. We have 1s2, 2s2, 2p6, and I do find sometimes when I'm doing these, especially with something with a larger electron configuration, if I'm going from orbital notation to electron configuration, I tend to sort of underline and bracket my orbitals, or my subshells rather, because it helps me. So 3s2, 3p6, 4s2, 3d, how many? 2, 4, 6. 3d6. Now, does anything look weird about that to you? Does anything bother you about that? Some people are bothered by this, some people are not. Pardon? Well, you can't combine anything, no. No, because you've got to list the subshells. The thing that gets at people is that, and that some people want to put all the threes together and put them in numeric order instead of filling order. You can do that after you write it. That's fine if you want to do the extra step. I think your book does that. I tend to leave them in the order they fill. I don't know that that's right or wrong. It's just how I've always done it. You'd have to ask a better chemist than I. So if you want to rewrite them in energy level order, you can. Whoops. You can't put a 2p after a 3s though. 3p6, 3d6, 4s2. What that means is you have to know that this is the one that isn't fully filled. So I think it's a little bit more sort of looking on your part, but that's okay. Okay, questions, comments, or concerns on this? What I'm going to do is turn you loose to practice on these. And tomorrow you're going to have a FIP quiz. There'll probably be 4 different elements. I'll say, you'll have to have your blank periodic table out. I'll have some extra copies. I will either give you an element name and ask you to do the orbital notation and electron configuration notation, or I'll say draw both of those for an atom with blank number of electrons. So pretty straightforward. It'll be paper and pencil, and you'll do it with the sub tomorrow.